So in the previous board, we learned histogram equalization and histogram specification, mapping, matching. Okay, and in this board, we will learn local histogram processing. So first we have to define and understand what is local histogram processing. We are defining here within the local histogram processing, we are defining a neighborhood and move its center from pixel to pixel. I'll explain this. See here. So this is the processing of local enhancement, local histogram processing. So actually we processed the methods which we previously discussed are the global methods. Means we are calling those two methods as global methods. Why we are calling them as a global methods means those are equalization and matching, nothing but the specification of the histogram of the image. We are calling those as global methods. So remember the word global means we are using generally everywhere in anything to process the image, to process and to apply any filter operation and any process operation upon the image. These basic things we have to do initially. That's why we are calling these as global methods for processing the histogram of the image. And there we modified a transformation function based on the gray levels, right? Based on the gray levels, we uh, modified the image by applying a transformation function within the entire image. And with the global approach, we got overall enhancement, not only upon a point, a certain point, a certain specific enhancement. We got overall enhancement upon the image. But in all other cases, in many cases, which is necessary to enhance details, specific details, a small area within an image. This we need in some cases to process this specific small areas of enhancement. We need to apply local histogram processing. So, how to do this local histogram processing? Here, we have one number of pixels in the areas, and those number of pixels, some areas of pixels are negligible. Those negligible pixels within the area of the image uh, are giving negligible influence on the computation of the global transformation. These. So, the shape does not necessarily guarantee to decide for the local enhancement. So, for this, we need a solution, and that solution comes from to devise a transformation function. Within the transformation function, we have to devise it for getting the solution. So, and the transformation function is based on the gray level distribution only. So, and we found other properties of the negligible pixel values on the area. Within that, a neighborhood of every pixel of the image we are collecting. Means, suppose this is the pixel, then the neighborhood of which is a specific one and a negligibly influenced one, that the neighborhood of the pixel we are picking. Okay, and the histogram processing technique is adaptable. Then if we collect the neighborhood of the every pixel within the image, then the local enhancement uh, is easily we can adapt. So the procedure to do this local enhancement to pick the neighborhood of every pixel is the procedure defined within by using a square or rectangular neighborhood. By these two operations, we can get local enhancement histogram processing. Within these two, a square or a rectangular neighborhood operation, within this we are moving the center. Remember here local histogram processing, we are moving the center by using the square or a rectangular neighborhood operation of the area from pixel to pixel. We are moving, first we are selecting the center and we are moving center pixel by pixel within the image, and we are selecting neighborhood pixel values. At each location, histogram points in the neighborhood is computed, and either a histogram equalization or a histogram specification we apply after processed after taking center and collecting neighborhood operations by using square or rectangular. Then a transformation function, we will got a transformation function within the equalization or the histogram specification, and then finally we use it to map the gray levels of the pixels which are centered in the neighborhood. This is nothing but the local histogram processing, and in this procedure, in this method, uh, actually we used previously two global histogram equalization and the specification. So with that we modified a transformation function. Now it is within the local histogram processing we used the square or a rectangular. Then based on gray level content of an entire image, then the global approach is suitable for overall enhancement when we applied local histogram processing. So, in this case, it is necessary to enhance details over small areas in an image. Then, within the small areas of image also, we can uh, get more information, more details, more enhancement by this local histogram processing. And the number of pixels here uh, we have, those are negligible influence upon the computation of a global transformation. Those also participating to contribute the shape, and which is not necessarily guarantee the desired local enhancement, but it is giving our requirement. So the solution is to devise a transformation function. Then the total solution depending upon the transformation function only. Now, now see the actual shortcut procedure step by step. So local histogram processing, within local histogram processing, we are moving, okay, we are moving, it's a center. We are moving the center from pixel to pixel within the image, and within by the movement of the pixel from the center at each location, the histogram points in the neighborhood is computed. All the neighborhoods are computed from the center. And after that we are again moving that one. How we can compute means either using the histogram equalization or using the histogram specification transformation functions. These two we already discussed in the previous videos. See those one for the reference. And then we are mapping the intensities of the pixel centered in the neighborhood. Then move to the next location and repeat these points. This is the procedure to do local histogram processing. And suppose if you see here, this is the original image. Okay, see some data is missing, hidden within the original image. And this is the image resulted by the global histogram equalization. So now onwards we are calling the histogram equalization and the histogram specification as the global histogram. Global, okay. So this is the process done by the histogram equalization. And then we applied the local histogram equalization. This is the global histogram equalization which we discussed in the previous, and now upon this we applied the local histogram processing. Means we selected the center and moved the center from pixel to pixel and collected the neighborhood pixels and then computed by using either histogram equalization or the specification transformation functions. Here the square and the rectangular transformation functions. Then see, after applied the local histogram function processing, see the hidden ones which are negligible from the original image and within the global histogram equalization are enabled within the local histogram processing. Then to process this, what are the equations, mathematical equations, operations we have to apply? So recollect the equations from the previous videos. Average intensity value, actually our M is having sigma of R, the intensity values, and the probability density function of the pixel value, intensity pixel value. We know for this we got this equation. Mn is the size, M by N. And from this equation, we are calculating the average intensity value which is represented by the UN of R, which is from I is equal to 0 to L minus 1. You know this is the range. Recollect the information from the previous videos. We got the average intensity value R minus M per N into probability density function of the R. Okay, this is the average intensity function, and from this we are calculating the variance. You know the variance symbol is this one. So variance is the square part to the square, so that's why we are applying the average intensity function to the base 2, to the base 2, okay, upon the R. Then the range is same, and you know this is the formula, and par n is equal to 2 here. Then from this we are getting, by simplifying this, we are getting doubling the sigma values for M and N to process each pixel and moving each location the variance value f of x minus m whole power 2. Okay, now this is the basic variance function we got, and this is the average intensity function we got. Then from this, now we are applying upon local histogram statistics for image enhancement. the local average intensity. Here we calculated average intensity. Now we now calculating a local average intensity value. We know we are representing the output with S of xy, the center. And obviously the function is the same R, but here it is S of xy. So it is the S representing the neighborhood which we selecting, that is nothing but the output. And from here we are calculating the local variance because this is the local histogram processing, sigma square of S of xy. So here the base only we are the index value, subscript value only we are changing within this formula. S of xy sigma of Ri minus m S of xy whole square into probability density function for the S of xy upon the pixel value R. And I'll show another example using histogram statistics for image enhancement. So suppose this is the g of xy function taken f of x, where here the condition, the f function is selected for the condition m of s is less than or equal to k naught mg and k1 variance of g is less than or equal to variance of Sn is less than or equal to k2 variance of g. And otherwise, if this is not the condition, this is not the case, then otherwise it is simply the f of xy. And here the mg is the global mean value and variance of g is the global standard deviation value. And here they taken k naught is equal to 0.4 and k1 is equal to 0.2 and k2 is the constant values. K2 is equal to 0.4 and the function e is equal to 4. By applying these values and upon this condition, this is the sample sim image filament which is magnified approximately 130 by 130. Okay, in this way we can get local histogram processing. So we have seen local histogram processing, and then now we are seeing some filter operations. And these filter operations are spatial filtering. We calling it as a spatial filtering. So here we are applying some filtering operations. So a spatial filter which consists of a neighborhood and a predefined operation. Okay, so the spatial filter is consisting of a neighborhood, means a neighborhood pixel value, and a predefined operation. And these filtering operations are linear operations and non-linear operations. For the linear spatial filtering of an image of size m by n, with the filter of size m by n, the sizes are different. The expression for the linear spatial filtering is this one. So the output g of xy, the neighborhood value, pixel value, is defined with the expression s is equal to minus a to a, t is equal to b to b, w of st, s and t are the pixel values for the output image, and you know this, x and y representing the input image pixel values. This w is weight. So w of s comma t is multiplied with the function consisting of the predefined operation, which is x plus s comma y plus t. x coordinate, y coordinate. Then I'll show some example values. See here, this is the original image, and these are the image pixel values represented. This is the x coordinate, this is y coordinate, and we selected the filter mask here from the origin. Okay, from the origin we selected filter mask, which is 3 by 3. This filter mask is, we represented the filter mask W of s comma t, which is this. The coefficients, filter coefficients are this 3 by 3 matrix, you know. So the filter coefficients are first coefficient -1 comma -1, x coordinate, y coordinate, and second -1 comma 0, -1 comma 1. And here in this way the y coordinate is changing, and in this way the x coordinate is changing. 0 comma -1, 1 comma -1, and this is 1 comma 0, 1 1, 0 0, 0 1. These are filter coefficients. Remember these coefficients to do the operations, filter operations. And the function, the f function, is represented as x plus s. So for this, x minus 1, because x coordinate is -1, and y minus 1 because the y coordinate is -1. And in the similar way, this is this x minus 1 comma y, because x plus s comma y plus t, and x minus 1, this is, and this is this. And this way the pixels of image section under filtering, and then we multiply these two operations. And for the filtering operations we require spatial correlation and the spatial convolution. First, very simply I'll say what is convolution, which is a very important operation in the deep learning machine learning concept. The convolution is applied in the linear filtering of an image, and which is accomplished through an operation, okay, which is accomplished through an operation. That operation we are calling convolution. So what operation we are applying upon linear filtering is called the convolution. And this convolution is a neighborhood operation, because spatial filtering means first part is neighborhood, second part is operation. So convolution is a neighborhood operation in which each output pixel is the weighted sum, the W, remember the W, in which each output pixel is the weighted sum of neighboring input pixels. Then the matrix of weights is called the convolution kernel. So the matrix we represented for the W is the convolution kernel, and that you also call it as a filter. And a convolution kernel is a correlation kernel that has been rotated 180 degrees. Remember, convolution, in the convolution filtering operation we can rotate 180 degrees. Okay, remember this point, because in the correlation we cannot rotate the image. So correlation means it is also closely related to convolution. Correlation is also the value of an output pixel computed as a weighted sum of neighboring pixels. Same definition. Only the difference is that matrix of weights, the W, the matrix of weights. And in this case, the correlation kernel, this W, is not rotated during the computation. And during the computation in the convolution, we can rotate. And for the convolution and correlation, spatial correlation is defined as spatial correlation of a filter W x comma y of size m by n with an image f of xy denoted as W into f operation. So W into f operation is defined with this one. Previously you have seen. And the convolution, you can see convolution of a filter W x comma y of m by n with an image f of x comma y is denoted with the same W of x comma y into f of x comma y input image into weights, which is defined the same function, but here the rotation is possible. I'll show an example. See this example. See here. So actually this is the original f of x matrix. Here this one, okay, and this is the W weighted matrix we selected. These are the matrix elements. Now we have to multiply this. For that, first we are padded with the 1 at the center, because center pixel we are selecting. And then initial position of the W is this one. Okay, then apply the full correlation result. This will move to the center by applying some operations, transformations, neighborhood operations, and then cropped correlation result of this one is this. So rotate it, and then rotate the W, and then this will become this, and the matrix is rotated. Then now apply the full convolution for the 180 degrees, then crop the convolution result, then this is the output one. In this way the operations are changed. So far we discussed the spatial filter, and now we are discussing how to smooth an image by using spatial filters. Smoothing spatial filters. Smoothing filters, separate filters are there to smooth the image. Those are called smoothing spatial filters. Smoothing filters are used for blurring and for noise reduction. Okay, to blur the image, and for noise reduction also we use smoothing filters. Blurring is used in removal of small details and bridging of small gaps in lines or curves. It means blurring means when we remove very small details, some small negligible pixel values from the image. And suppose when we remove a small detail in the image, there is occupied by a gap. Those small gaps are bridged in lines or curves. Then the blurring is happening within the image. And smoothing spatial filters include linear filters and non-linear filters too. Then the implementation for smoothing linear filters for m by n size image with weighted averaging filters of size m by n is given by this formula. And this, this is the m by n, this this M by N smooth filtering operation previously we discussed, and this we dividing with the weight matrix W. And here this limitation minus A to A, B to B, A for the X, S means output X coordinate, B for the output Y coordinate. That size of the weighted average filter M is calculated as 2A plus 1 this, and N is equal to 2B plus 1 this. Now see an example for the two smoothing average filter masks. So this is one filter mask. For this we constantly multiplying one value so that all are resulting one only. And this is the second filter mask. We are multiplying this with the 16. These are two 3 by 3 smoothing filter masks, and I'll show another example how a filter is happened. See this here by the picture. Observe these pictures. Actually, this is the original 500 by 500 pixel original image, and these are the smooth after applied smoothing filters. These are the outputs. For these lines, the size is 3, 5, 9, 15, and 35 respectively. And the black squares at the top are 3, 5, 9, 15, 25, 35, 45, and 55 pixels respectively. And the borders are 25 pixels apart for these. And these are the values, mask values we applied. And the letters at the bottom are in the size of 10 to 24 points and increments of 2 points. Each is incremented 2 points with the previous one. And the larger letter top is 60 points. Vertical bars, these are 5 pixels wide and 100 pixels height. Their separation is 20 pixels. The gap between these are 20 pixels. And the diameter of the circles, these circles, is 25 pixels. And their borders are 15 pixels. And the intensity levels from 0 to 100, you can see for here it may be 0, here it may be 100 intensity values. Background image is 10% background. So whenever the black color background is 10%, then it looks like this, the gray color. And the noise rectangles are 15 into 120 pixel values. In this way, after applying a smoothing filter upon the original image, these many different types of output images we can get. Another example I'll show you here, the gross representation of objects. This is the image of 528 by 485 pixels from the Hubble Space Telescope, and this is the filtered image of a 15 by 15 averaging mask, and this is the result of thresholding of this one. So observe the output and see for what values the smoothing filter giving the output of the image for the original image. Now see non-linear filters. We also call these as order statistic filters. The order statistic filters we are calling non-linear filters. Commonly well-known term is a non-linear filters. Uh, up to now we discussed linear filters. Now we are discussing non-linear filters. Why these are order statistic means they are based on some order, some ranking they are following the pixels contained in the filter mask. We applied previously 3 by 3 matrix mask for the filter. Within that filter mask, we are following some order, some ranking, and replacing the value of the center pixel. Remember, we are replacing the value uh, at the center pixel with the value determined by the ranking result. Okay, and these ranking results we are replacing the center value by determining that ranking result by median filters, max filters, min filters. We are applying these operations. And see, these are the examples. Actually, this is the X-ray of the circuit board, and this X-ray of the circuit board is corrupted with the salt and pepper noise. Okay, and this noise is reduced by averaging mask, and this is the resultant one. When we apply averaging mask of 3 by 3 averaging mask, then from this is the resultant one. And if we apply noise reduction with the median filter, then this is the resultant one. So median filter is better. Then for sharpening spatial filters. Sharpening spatial filters, for to sharpening the images, we are applying spatial filters. Those are called sharpening spatial filters. First, we have to do foundation. Okay, and after that, we have to do Laplacian operator, Laplacian mathematical equation, and then unsharp masking and high boost filterings we are applying, and we are using first order derivatives for non-linear image sharpening. The first order derivative for nonlinear sharpening, we using the gradient method, which is a very popular method, optimization method we use within the deep learning, very important one this. And how to do, first is the foundation. How to do the foundation here. The foundation for sharpening the spatial filter. The first order derivative of a one-dimensional function f of x is the difference. Okay, so the first order derivative is the difference of dou f by dou x. So the f function, this with respect to x, is the first order derivative, is defined as f of x plus 1 minus f of x, the difference, the first order derivative of the difference. So we are uh, subtracting from incremental function from the original function from the incremental function x plus 1 minus x, like that. And second order derivative for this one is the derivative of f of x as the difference of dou square f by dou x square. This is the second order derivative, dou square f by dou x square. From this, the second order derivative is defined as expressed as f of x plus 1 plus f of x minus 1 minus 2 f of x. Now, if we see these foundation formulas, first order derivative and second order derivative, if we apply, see how we will get the points. So suppose first and second order derivatives of a one-dimensional digital function representation representing a section of a horizontal intensity profiles from an image. So these are the intensity values and these are the scan line values. For these, okay, first intensity values, so 6, 6, 6, 6, so up to 4 points it is constant intensity values. And now here it is changed. So this is the intensity transition point. This is the intensity transition point. This one. And in remaining points, and here the value is changed from the constant values to it somewhat degrading. So, and after observe the values 5, 4, 3, 2, 1, 3, 2. So, up to here, this is 5, 4, 3, 2, 1, and 1. So, up to here, the values are, this is 6, okay? This is 6, 5, 4, 3, 2, 1, okay? This, the values are decreased. So this type of edge we are calling ramp edge. Whenever it is falling down from certain constant intensity transition position is happened at the 6, and from constant intensity, whenever the edge is falling down, pixel values are falling down, then that is called the ramp. And then again there is a constant intensity values up to here. So again constant intensity value, and here it is raised, and again it is constant intensity values. Then raised is edge we calling step, falling is called the ramp and raised one is called the step. And we discussed the first differential equation, first derivative. From that equation, these are the values for these intensity values, and for the second derivative, these are the values we can get from that formula. And by these values, first derivative values, second derivative values, from these x original intensity values, we are plotting the graph, and see the empty squares are the second order derivative and these are the first order derivative, and these are first and second order derivative both. So this is the plotting of the graph for first order derivative, second order derivative of the intensity pixel values. We calling it as a scan line. Then, so this is the basic thing to sharp the spatial filter of the image. Now with this first order, second order derivative, now we have to take a Laplace operator. Up to now foundation is completed, first order derivative, second order derivative. Now Laplace operator. So the second order isotropic derivative operator is the Laplacian for function f of x comma y, which is nothing but our image representation. And this second order isotropic derivative operator, nothing but the Laplace operator, is defined as dou square of f is equal to dou square of f by dou x square and plus dou square of f by dou y square. Here this f is with respect to the x and this f is with respect to the y, because we have a two coordinates x and y, and the second order derivative dou square. And this the expression for this, we have seen this is the expression, and for this is the expression, and now we have to add both the expressions, these two. So x plus 1 comma y this, x minus 1 comma y this, and f of x comma y plus 1 is this, and x comma y minus 1 is this, and minus this 4 f of xy. This is the expression by combining these two. This is the Laplace formula, operator formula to sharpening the spatial filter of the image. Now, suppose we apply these formulas for this mask value. This mask value. This is the mask value, filter mask we want to implement. So from this, if we implement an extension of this equation, it includes the diagonal terms these, and these two are the first order implementation of the Laplace Laplace operator giving these two values. Then for these, how to sharpening the spatial filter using Laplace operator means the sharpening of the image is using a Laplacian is g of x comma y. Output image is equal to f of x comma y input image plus some constant value c and dou square of f of x comma y means second order derivatives of the f of x comma y from here. So f is a input image, g is an sharpened output image, c is equal to -1 if second order derivative is correspond to these values, and if c is equal to 1, we can use either of the two filters. And now I'll see an example. See, I think it is clear. See, this is the original image and this is the Laplacian scaling image, and this is the Laplacian image sharpened image using some mask scaling image. This is without scaling and this is with the scaling, and this is sharpened image with the mask value. By all this is the resultant output image. So we have seen Laplacian scaling and Laplacian operator. Now see unsharp masking and high boosting filtering. What is unsharp masking? So suppose sharpen images consists of subtracting an unsharp smoothed version of an image from the original image. It means whenever we are sharpening an image, then first we are applying some mask upon that. So we are blurring the image. Then we are applying some Laplacian operator formula expression upon the image and removing that too and sharpening the image. So this is unsharping masking. So here we applied some mask. So the steps for unsharp masking are: first we have to blur the original image and then subtract the blurred image from the original image. Add the mask to the original image. These three are the steps. Now I'll show the expressions we used to unsharpen the image. So for the high boost filtering, suppose let us take the inverse of f of x comma y. F dash of x comma y denotes the blurred image because it is imposed by the blurredness, some mask upon that. It is not the f of x, it is the f dash of x comma y denoting the blurred image. Unsharp masking means here we are taking the mask. So the unsharp marking is defined with the expression, and unsharp masking is denoted with the g of mask of x comma y, and it is defined with the expression f of x comma y minus f dash of x comma y. We already discussed we are removing the unsharped image, blurred image from the original image, and then add a weighted portion of the mask back to the original one. So some mask we have to add to the original image, that is a weighted portion of the weighted mask. So g of x comma y representing the sharpened image, f of x it is denoted with the expression for the addition of weighted portion of the mask. F of x comma y is added with here see added with k into g mask of x comma y. So this one blurred image. Okay, here k is greater than or equal to 0 always. When k is greater than 1, the process is referred to as high boost filtering. So k is great. This is the weight we are adding. So this weight k is greater than or equal to 0 commonly. Whenever it is k greater than 1, the process is referred to high boost filtering. And now I'll show some examples. Here see, this is the original signal. Okay, this is the demo for unsharp masking example, and for this original signal we are blurring the signal. See, these dashed lines are the original signal and we blurred with these curve signal, and then unsharp masking. So this is the mask we are applying upon this and then adding this. Then this is the sharpened output g of x comma y. I'll show with an not by the signals, by the image. I'll show an example here. See this. This is the original image. So we are unsharping masking and high boost filtering. Example is this. So for this original image, when applying blurring, how we can apply blurring? By using some Gaussian filter Then by the result of Gaussian filter, this is the result of blurring image for this original image. And then we unsharped this image, then this is the result one. Then we unsharpen masking by adding a weight, then this is the result one. Then apply the high boost filter, then this is the output image. See the clarity between each and every step. Now we will discuss some other filtering operations like a Sobel gradient, those sharpening first order derivatives. So image sharpening based on first order derivatives. Uh, we know this is the function. For this function, the gradient, okay, see, don't take this gradient means some other else complex meaning. A gradient means a small part of the image, okay. The gradient of f at coordinates x comma y is defined with this equation. See, a gradient of f is representation of image. Image is represented two-dimensional with x coordinate, y coordinate. At that point, some part, some smallest part means the gradient, called the gradient, is defined with this. So delta of f means gradient of f. So this is the representation of the gradient of f is gx by zy is equal to first order derivative of dou f by dou x, dou f by dou y. This is the x coordinate with respect to x coordinate. This is the y coordinate with respect to y coordinate. Very simple. And the magnitude of vector is denoted by the m of x comma y. Now the gradient image m of x comma y is the magnitude of the gradient of f. This is expressed as square root of gx square plus gy square. This is the expression for gradient image magnitude of f. Now based on these formulas, see how to calculate. So image sharpening based on first order derivative, how to calculate the magnitude. First we have to derive the formula. How to derive the formula? The magnitude of vector delta of f denoted as m of xy as here. M of x comma y is a magnitude of delta of x vector of f is we defined with this expression from here. Then this is similar to absolute values of g of x plus absolute value of g of y. See, this is square and this is square root get cancelled out, and it is the absolute value of g of x and absolute value of g of y. Then this is represented with the coefficients. Suppose these are the matrix coefficients 3 by 3. It is the mask. Okay, it is the mask, suppose. Then here it is defined as Z8 minus Z5 is the g of x, and which is added with the Z6 minus Z5. This is the y. G of x, g of y. See, this is subtracted with the center point, and this is subtracted with the center point. Okay, then from this formula, remember this, from this formula, see different approaches to sharpening the image based on first order derivatives. Here first is the Roberts cross gradient operator. Okay, Roberts cross gradient operator is denoted with the Z9 minus Z5 plus Z8 minus Z6. This is cross subtraction. Okay, this is the Roberts cross gradient operator. Remember this. Z9 is subtracted with the center pixel. Z8 is um, cross. Okay, within the mask, the cross subtraction. Z9 minus Z5, Z8 minus Z6 plus. This is g of x. This is g of y. X coordinate, y coordinate. Roberts cross C. Cross. Clear? Now, Roberts cross gradient operator. So whenever you got the question Roberts cross gradient operator, you have to mention this expression. And to apply Roberts cross gradient operator upon the image, use this expression within your code. And then Sobel operator, important one. Sobel operator is another filter operation for sharpening the image. This is defined as, don't confuse the explanation, listen carefully. Sobel operator is defined as Z7 plus 2Z8 plus Z9. Okay, center one is multiplied with the 2. Minus means last row is subtracted by the first row. Z1 in the same way. Z1 plus 2Z2 plus Z3. Okay, and this is added. So up to here x, g of x is completed, and now the plus addition, and third column is subtracted from first column. This is y, g of y. Okay, so z3 plus 2z6 plus z9 is subtracted from z1 plus 2z4 plus z7. In this way, remember the formula of Sobel operator and apply within your code this expression. You will get Sobel filter upon the image. And I'll show the examples for these Roberts cross gradient operator and Sobel operator. This is an example. So these are the Z values, and Roberts cross gradient operator is this one, and this one. This is x and this is y. Now we are applying Sobel. Sobel is giving the output for x is this and for y is this. And upon image, I'll show this is one image. This image giving, this is the input image by the Sobel operator, Sobel gradient. This is representing 4 o'clock, 5 o'clock. Okay, sharpened 4 o'clock, sharpened 5 o'clock representation. And I'll show another important application example. See this. So this is the original image of a whole body bone scan. Upon this, we applied some Laplacian operator. Then this is the Laplacian operator output. To that, we sharpened the image by adding these two by using the Sobel gradient. So this is the output of Sobel gradient. See, image is sharpened, enhanced by the image by sharpening it and bringing out more of the skeleton details than the input image. And from this, see, combining the spatial enhancement by using the averaging filter, Sobel image is smoothened. Then mask image formed by product of these two. Then it is again sharpened and again it is applied by the uh, uh, power law transformation. Then this is the power law transformation. Image is more enhanced and more sharpened and brightened out more skeletal details. This is the application. So in this board we covered the topics local histogram processing, average intensity by the variance, and spatial filters correlation, spatial filters convolution, and smoothing linear filters. See, this correlation and convolutions we will apply within the deep learning processes, machine learning, and smoothing linear filters, non-linear filters, median filters for noise reduction, sharpening spatial filters, Laplace operator by using, and unsharp masking and high boost filters we applied, sharpening using first order derivatives and magnitude vector also we discussed, Robert cross gradient operator, filter Sobel operator. These we discussed and we will meet in the next lecture.